Welcome to AI Infra Not Not 7 YouTube channel. If you're an infrastructure engineer, cloud engineer, or SRE working in enterprise IT, you probably heard people constantly talking about AI, GPUs, and AI factories. That raises an important question. Are traditional enterprise servers going to be replaced by AI servers? In this video, we'll compare traditional servers versus AI servers, look at what's really happening in today's enterprise data centers, and separate the facts from the hype. Let's get started and happy learning. Let's compare the architecture of a regular enterprise server and an AI-accelerated server. On the left is a regular enterprise server. Its main processor is the CPU. A CPU is designed to handle different types of tasks one after another. For example, a user opens a website, the server checks the database, processes a request, and sends a response. The same server can also run virtual machines, storage services, and many other business applications. That's why CPUs are called general-purpose processors. Now look at the AI server on the right. Instead of relying mainly on CPUs, it is built around multiple GPUs. GPUs are designed to perform thousands of similar calculations at the same time. That's why they're ideal for AI workloads like image training and text inference. The GPUs are connected using a very high-speed NVLink fabric, allowing them to share data quickly while working together as one powerful system. Think of it like this. A CPU is like one skilled office worker handling different jobs one by one. A GPU is like thousands of workers doing the same job in parallel. Asterisk, asterisk. So, the architecture is different because the workloads are different. Regular servers are built for everyday enterprise applications, while AI servers are specially designed for large-scale AI processing. Now that we understand the difference between a regular server and an AI server, let's look at the main building blocks of an AI server. First is the CPU. Think of the CPU as the head chef in a restaurant. It doesn't cook every meal, but it manages the kitchen, organizes the work, runs the operating system, manages storage, and sends data to the GPUs. In short, the CPU controls the entire server. Next is the GPU. If the CPU is the head chef, the GPU is like thousands of sous chefs working at the same time. Instead of handling one task after another, GPUs perform thousands of calculations in parallel. That's why they're perfect for AI workloads such as training large language models and image recognition. Now let's talk about HBM or high bandwidth memory. This is ultra-fast memory placed right next to each GPU. Imagine every chef having a fully stocked pantry beside them. They don't have to walk across the kitchen to get ingredients. This allows the GPU to receive data instantly and keeps it working at full speed. Next is NVLink. This is a high-speed connection between multiple GPUs inside the same server. Think of it as a private express highway that lets GPUs share data quickly without traffic delays. Then we have NVSwitch. If NVLink is a highway, NVSwitch is the traffic controller. It ensures every GPU can communicate with every other GPU efficiently, without creating bottlenecks. Finally, there's InfiniBand. While NVLink connects GPUs within one server, InfiniBand connects thousands of AI servers together. Think of it as a super-fast transportation network connecting multiple restaurant kitchens into one giant AI factory. Together, these building blocks make modern AI servers powerful enough to train and run today's most advanced AI models. If you work with Dell PowerEdge, HP ProLiant, or Cisco UCS servers, this board shouldn't look unfamiliar. At the end of the day, it's still a server motherboard. The difference is that it's purpose-built for AI workloads. At the center is the NVIDIA Grace CPU, which runs the operating system and manages the entire server. On the left are two NVIDIA Blackwell GPUs, NVIDIA's latest generation of AI GPUs. Each GPU contains hundreds of billions of transistors, tens of thousands of CUDA cores, and HBM3 high-bandwidth memory, providing enormous parallel computing power for training and running large AI models. Don't worry if terms like CUDA cores or tensor cores are new to you. We'll cover them in detail in an upcoming video. Between the CPU and GPUs are the NVLink fabric switches, enabling ultra-fast communication between all processors. On the right are the CPU memory slots, and at the bottom you'll find the familiar network, storage management, and power connections. So, while the motherboard layout looks familiar, the biggest difference is that the CPU, GPUs, memory, and networking are all optimized to train AI models at massive scale. That's what makes an AI server fundamentally different from a traditional enterprise server. Let's compare the software stack of a regular enterprise server and an AI server used for training large language models. On a regular enterprise server, the bottom layer is the physical server. Many organizations install a hypervisor, such as VMware ESE, and create virtual machines. Others install Linux directly on the hardware. Above that is the operating system, such as Red Hat Enterprise Linux or Ubuntu. Next comes the platform software like Apache, Tomcat, Jinx Oracle Database, PostgreSQL, or MySQL. Finally, at the top is the business application, such as an online banking system, ERP application, e-commerce website, or payroll system. The application stores and retrieves business data from the database. Now let's look at an AI server. Most AI training servers run Ubuntu Linux directly on bare metal to achieve maximum GPU performance. Instead of web servers and databases, they install CUDA and CCL and AI frameworks like PyTorch or TensorFlow. At the top, instead of running a business application, the server runs an LLM training job. The input is massive datasets, and the output is a trained AI model. So the architecture is actually very similar. The operating system is still Linux, but the software above it changes completely, from application software to AI frameworks designed to train large language models. Let's compare a typical enterprise server with a modern AI server. Both servers have CPUs and memory, but they're built for different jobs. A traditional enterprise server runs business applications, databases, and virtual machines. An AI server is designed for massive parallel AI processing using multiple high-performance GPUs. Now, let's look at the biggest differences. Networking is one of them. Enterprise servers typically use 10, 25, or 100 gigabit Ethernet. AI servers use multiple 400 gigabit InfiniBand or ROS connections, allowing thousands of GPUs across many servers to exchange data at incredible speeds. The next big difference is power and cooling. A regular enterprise server consumes about 500 watts to 1.5 kilowatts, but a modern AI server can consume 10 to 12 kilowatts. To put that into perspective, one AI server can use about the same continuous power as 5 to 10 average US homes combined. And because almost all of that electrical power becomes heat, the server also needs cooling capable of removing 10 to 12 kilowatts of heat. That's why AI data centers use liquid cooling or rear door heat exchangers instead of relying only on standard server fans. Finally, let's talk about cost. A typical enterprise server may cost between $8,000 and $25,000. A modern AI server can cost $350,000 to over $550,000 for a single node. So, AI servers are not simply more powerful servers. They require special networking, dramatically higher power, advanced cooling, and a much larger investment, making them a completely different class of infrastructure. A question I hear a lot is, are regular servers going away because of AI? The answer is no. Let's look at what enterprise data centers actually look like today. First, in a typical enterprise, such as a bank, hospital, retail company, or manufacturing business, 95 to 99% of physical servers are still traditional servers. These handle business applications, databases, virtualization, storage, backups, and network services. AI GPU servers account for only 1 to 5% of the total. Next, let's look at large cloud companies. Here, AI adoption is growing faster. Around 80 to 95% of servers are still traditional compute servers, while 5 to 20% are AI GPU servers used for AI training and inference. Now consider AI-first companies such as OpenAI, Anthropic, xAI, and AI Research Labs. Since AI is their primary business, 30 to 60% of their infrastructure can be AI GPU servers, with the remaining 40 to 70% being traditional servers. Here's a simple example. Imagine an enterprise with 2,000 physical servers. It might have 900 application servers, 500 VMware hosts, 200 database servers, 150 storage and backup servers, 150 network and security appliances, and only 20 to 50 AI GPU servers. So, while AI infrastructure is expanding rapidly, regular servers are not going away. They continue to power most enterprise workloads, and AI infrastructure is being added alongside them, not replacing them. Thanks for watching AI Infra Not 7 YouTube channel. Happy learning, and I'll see you in the next video.